Today's lesson is called Vertical and Horizontal Shifting of Functions. So if you are starting to watch this video, that means you must have already completed the vertical and horizontal shifting of functions Desmos that was assigned to you. It is extremely important that you complete that Desmos investigation first and fill in the first page of these notes for investigation number 1 and 2 so that we can go over these answers quickly and move on to examples of vertical and horizontal shifting of functions. So if you have not completed the vertical and horizontal shifting of functions Desmos, please stop this video, go to Google Classroom and complete your assignment, then come back here to check your answers to the investigation before moving on with me. If you did complete your Desmos already, that means you're ready to go over the answers. So it says we can build new functions from others by various types of transformations. Using Desmos, we will investigate how vertical and horizontal shifts affect the graph and equation of different functions. So in the previous lesson, we looked at all of the parent functions, the most basic versions of the functions that we have learned about with a couple new ones thrown in. Those parent functions are what we're going to be manipulating in order to figure out what happens to these functions when you do certain shifts or changes. So in investigation 1, the investigation had you add and subtract on the outside of the parent function. You used f of x equals x squared in both cases, and you were either adding a positive number on the outside or you were adding a negative number on the outside. So you were adding or you were subtracting. And again, you see that I have highlighted outside. You might want to do the same thing. When you completed slides 1 through 6 with adding on the outside, the big idea you should have gotten is when k is positive, the graph shifts k units up. So as you can see, I added an example. I would like you to add this into your notes as well. So an example of a vertical shift up would be taking f of x equals x squared, the parent function, and doing g of x equals f of x plus 2. Adding on the outside moves the function up. In part B, you added a negative on the outside, so you can write down the example that I have there, h of x equals f of x minus 3. Whenever you add a negative, or in other words, subtract on the outside, the graph shifts k units down. So when k is negative, the graph shifts k units down. So adding on the outside, you go up. Adding a negative or subtracting on the outside, you go down. Now we'll look at investigation number 2. Let's investigate the effect of adding and subtracting on the inside of our parent function. So there were a couple slides that asked you to do this and make a guess and then see what the actual answer was. And the question here was, what surprised you about your findings? What I hope you saw is that it actually acts the opposite of what your gut feeling would tell you. So let's look at part A. Using the parent function f of x equals x squared, let's build a new function j of x equals f of x minus h squared. So when you did this investigation, when you dragged the slider to an h value that had a positive number, that really makes it minus inside of the parentheses. So x minus 4 actually moves the graph to the right 4 units. So a subtraction inside the parentheses actually means you're going to the right. In part B, using the parent function f of x equals x squared, let's build a new function. So once again, we were dragging the slider for h, but this time if I dragged the h value to a negative number, for example, negative 2, which I then put in h's spot into the equation here in orange, you can see that those double negatives are really going to change this to f of x plus 2. So that means we have a plus 2 on the inside of the parentheses, but we actually go to the left. So overall, if it happens on the outside, it goes with exactly what your gut should be telling you. Positive is up, negative is down. When this adding or subtracting happens on the inside of the parentheses, it's the opposite of what your gut would tell you. Normally when I see a negative, I think left, so it's actually going to move to the right. And vice versa. When I see a positive on the inside, I'm actually moving to the left. So let's go on together and look at some examples of what we saw in the investigation in action with different types of questions asking us to do different types of things. In example 1, it says the parent function f of x equals x to the third power x cubed. That is going to be our parent function, is shifted 8 units left and 2 units down. Write the equation for the new function. So the first thing I want to make note of here on the side is that since the parent function was already called f of x, we want to make sure we use a different function name. Just a different letter of the alphabet would be fine. So let's write must use a function name that is not f of x. So since f of x was already used, we will pick a different letter. So I'm going to pick g of x. Does not matter what you pick, and I'm going to say it's equal. We have to figure out how these shifts affected the function and the equation. So let's go piece by piece here. First, I'm going to look at what happens in the first statement. It says it shifted 8 units left. So from what I remember from my investigation, if anything's going left or right, that's happening on the inside. Then I see they also want me to go 2 units down. From my investigation, I know anything up or down is happening on the outside. So first I want to decide where I'm going to put it. Then I need to think about what sign goes with it. So I know on the inside, I'm going to have an x, something, parentheses, and cubed, because the original parent function was cubed. I went 8 units to the left. So that means I'm going to do the opposite sign of what my gut would tell me. Usually the left is negative, so we're going to make it positive. And since it's 8 units left, I'm going to do plus 8 on the inside. So this inside is correlating to this positive 8 here. Then, because it was 2 units down, outside acts as if it should. Positive is up, negative is down. So when I see 2 units down, I know I need to subtract 2 on the outside. And this is now my new function with the transformations that have occurred. In example 2, it says the function f of x equals absolute value x, and it is shown graphed. So you can see that picture to the right. The function g of x is defined by g of x equals f of x plus 3 minus 6. They want us to produce a formula for g of x and graph it on the grid provided. So let's highlight those portions. We're going to produce a formula and we have to graph it. So the first thing I want to do is take a look at the formula. My parent function is f of x equals the absolute value of x. They gave me g of x equals f of x plus 3 and then minus 6. But we already know f of x is absolute value x. So I want to make that connection right here that we have to do some substitution. G of x equals f of x plus 3 means that we have to sub x plus 3 in for x. So my g of x is really g of x equals, instead of writing f of x plus 3, we know f of x is the absolute value of x, so we're going to write absolute value of x plus 3. And that then has minus 6 on the outside. So looking at that, I can now break this down. If I'm adding 3 on the inside, it's opposite of what my gut would tell me. So I'm actually shifting to the left 3, and anything on the outside goes with exactly what we would think. If it's negative, that means it's going down 6. So we wrote the formula properly by doing the substitution. And now we need to actually create the graph on the grid. So when you do this, you want to identify some critical points. So I'm going to go to the parent function and identify several critical points so that I can have something to look at to create my new graph. We already decided by looking at the formula that it was a shift left 3 and down 6. So I'm going to take every single point and shift it left 3 and down 6. So 1, 2, 3 to the left, 1, 2, 3, 4, 5, 6 down. And I'm going to do this for every single point. So 3 to the left and then 6 down. 3 to the left, 6 down. 3 to the left, and then 6 down again. And then I have one more point that I want to do the same exact thing for. And then once I have those, I can connect them. To make my graph. We'll make this a little wider so that you can see it. Same thing here. Make sure we have arrows on the ends. And then we want to make sure we label this with our new function, which is g of x equals the absolute value of x plus 3 minus 6. So now with learning this, I'm hoping that you're seeing these absolute value graphs that we used to have to break up into pieces to write the equations for. We can now just look at how it's been transformed from the parent function and be able to quickly come up with an actual absolute value equation for these new pictures, which is something we were not able to do before. Let's look at part B now. So in this part A, we had to create the graph. In part B, the graphs are created for us. So it says two functions, f of x and g of x, are shown below. Write a formula for g of x. So f of x is already on the graph. I'm going to pick a critical point, 0, 0, and I want to see where that point has landed in the new function g of x, which is right here. So it looks to me I had to go up 1, 2, 3, 4, 5, 6, and then I had to go 1, 2, 3 to the right. So that was up 6 and right 3. So we now have to show that in our formula. So I'm going to do g of x equals. This function was not told to us. I do not know what parent function this is. They didn't call it a quadratic. They didn't give me an equation. I have to remember back from our work with parent functions which one this is. So after our lesson on parent functions, I'm hoping that you recognize that this is the square root function. So this f of x is really f of x equals square root x. So we want to manipulate that going up 6 and right 3. So I'm actually going to talk about the right 3 first because we know that has to go inside. So inside also could mean under a square root or a cube root symbol. So right 3 is really going to be subtracting 3 underneath that square root symbol. And then up 6, we will add 6 on the outside. Now I'm writing it really spaced out to make sure that the audience, whoever's reading my paper, understands that that 6 is happening on the outside of that function, not underneath that square root. Now let's move on to our final example, example 3. The function f of x is shown graph below. As you can see here, it's a piecewise function. So we don't have a formula for it. They're just going to refer to it as f of x, and that's fine because we can still figure out the transformations from g of x, which they give us as f of x minus 5, then minus 3. So the first question says, how will the graph of g of x compare to that of f of x? So I want to take that formula and write it down. G of x equals f of x minus 5 and then minus 3. So let's talk inside and outside. On the inside, I see I'm subtracting 5. So remember, anything on the inside happens the opposite of what your gut would tell you. So that means we're actually going to the right 5. So this is a shift. right 5. And then we'll go highlight our other portion here that was on the outside, which was minus 3. And we will say that this, remember, happens exactly as it should. Negative means down. So, and 3 units down. So it's going to shift right 5 units and 3 units down. So once again, I'm going to find those critical points, but if I look at the graph, I find that they've already done that for me. I see that we have 3 points on the original piecewise function, and those are the ones I'm going to use to make my shifts. So I'll start with negative 7, 2. I'm going to shift that right 5 units and down 3. Then I'll go to the next point at the peak, which is at negative 3, 8, and I will shift it 5 units to the right and 3 down. And then my last point, same thing. I'll go 5 units to the right and 3 down. I'll then connect it in the exact same shape that it was originally. Again, let me change the style to be a little thicker so you can see it nicely. And this time I am not adding any extra arrows because there were not arrows on the original piecewise function in front of us. Okay, so we just took care of part B, which was draw a graph of g of x on the grid. And that concludes our lesson on vertical and horizontal shifting of functions.